Hello, this is Josiah Winslow recording for his Programming in Java course at METC for instructor Mark Cribb. Now, this week we have been given 3 different programming challenges. Well, it used to be 3, now it's 2, but I decided to add the third one back in. And they're all about recursion, which is chapter 15 in our textbook. And we were also given one database challenge where we have to use Java to connect to a database and do certain operations on object data. I'm still relearning how MongoDB works, so I'm saving that for later, and I'm doing the recursion challenges now. Now, by the way, these are some of the simplest challenges that we've ever gotten, not necessarily conceptually, because, it might take a while to wrap your head around it, but definitely in terms of actual code being written, it's one of the simplest challenges we've gotten. And you'll see what I mean in a sec. So here we have the entire code for the first challenge. Here we have the entire code for the second challenge. And here we have the entire code for the third challenge. As you can see, they are very small. Now, by the way, these are just the challenges by themselves. I'm writing more code that's basically boilerplate to run these, to choose which one to run and then run them. But I've discussed that in other videos before. I don't need to go over it again. So this first challenge is a recursive multiplication challenge. We have to write a recursive function that accepts 2 arguments and returns the result of multiplying them together. Keeping in mind that multiplying, say, 7 times 4 would be the result of adding 4 to itself 7 times. Now we have to use recursion. We can't use the actual multiplication operator itself. So what I do to recursively do this is, if either of the arguments is 0, I return 0 because that's the definition of multiplying by 0. If either of the arguments are negative, I make that argument positive and then negate the result. And then, here I could do just either one of these things, but for the smaller number, that would take, fewer recursive calls to itself if I were to decrease the smaller number instead of decreasing the larger number. So whichever one the smaller number is, I decrease that, call it again with the other argument, and then add the other argument to it. So for example, for 7 times 4, what that would mean is 7, that's the x here, let's say, 7 plus whatever 7 times 3 is. And 7 times 3 would be 7 plus whatever 7 times 2 is. And so on and so forth until 7 times 4 would be basically just adding 7 to itself 7 times. Or 7 to itself 4 times. Excuse me. Now how I'm choosing to test this out is with this. So you see right here, I have 20 trials. Can't talk today. 20 trials of multiplying different numbers from negative 10,000 to positive 10,000. And what I do is I get random numbers within that range, multiply them together using the multiplication function, and print out the result. So let's go ahead. And here we go. Here are the results of multiplication by different random numbers. Now, obviously, the recursive algorithm poses a bit of a problem if you go too deeply. Like, for example, if I increase the bounds, then at some point, here we get like a giant, scary error message that's basically Stack Overflow, which it is, in order to have so many recursive calls to a function, it has to store where to jump back when the function is done onto a giant stack. And that stack has basically overflowed. It has gotten so big that the amount of storage allocated for it cannot hold all of the different return addresses, so it's just exploding because it's having to call itself so many times. So that's one of the limitations, is you can't recurse too far with a recursive algorithm, though. Once you get into the mindset, it's easy to think of ways you could make something recursive. In fact, that's what I did for this challenge. This actually doesn't have much to do with recursion at all, because this is just a palindrome detector. We have to write a method that takes a string and determines whether or not it is the same as its reverse. And you could do that many different ways, none of which has to involve recursion. But as a challenge to myself, I decided to implement it in a recursive way. So here's what I decided to do. So here we have is palindrome, which takes a string s, and then it calls a version of itself that I've overloaded with indices, which start out at the left edge and at the right edge of the string respectively. So I starts at 0 and j starts at the length -1 because that's the last index. And here's what I do with that. If I is greater than or equal to j, then we're at the middle of the string, and by now we've verified that this is a palindrome, so we return true. Now, if it falls through there, then if the characters at the indices are not equal to each other, we stop there because it's not a palindrome, and we return false. And then finally, we return the same function called on the same string, but with the left index pushed 1 index to the right, and the right index pushed 1 to the left. So it basically burns the candle at both ends, checking to see if the characters at the ends are equal to each other, and if they're not, then it's not. But if they meet at the middle, then it is a palindrome. So what I decided to do to test these out is, here I have a few strings that are the same as their reverses and will return true, and I have these which will return false. The Fortnite cube, Kevin. And for each of these, I do the test, and if it is a palindrome, I print this phrase is a palindrome. Otherwise, I print this phrase is not a palindrome. So let's go ahead, and we should get true, 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 false, 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 false. And here we go. True, 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 false, 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 false. And by the way, something like this, if you do the letters, and only the letters, forwards and backwards, then they are the same. So that would make this a palindrome in the colloquial sense, but that's not exactly what the challenge was asking. So this with the capitalizations and also the comma right here, they just don't match when you put them side by side. And the last challenge we're going to go through today is the Ackermann Function. So the Ackermann Function is a recursive mathematical algorithm that can be used to test how well a computer performs recursion. And what I got from that is, like, you can optimize out some of the recursive steps when you do something like this. And so here we get the logic of the Ackermann Function, which is very easily translatable to Java. In fact, here it is. Very, very similar. If you can see both of them. And how I decided to test that is, we are given a few test cases that we are supposed to try out our method with. And here we are. I have them all in like an array of arrays of integers. And I have a list going through, or a for loop going through all of them in the list, and then taking the arguments, doing the function, and outputting the result. There we go. And I checked on Wikipedia and elsewhere to see the proper values of these functions, and it all checks out. So yeah, these were pretty fun challenges, and I was able to do them quite easily. And the database challenge I will do very, very soon. I just thought that I should get this out of the way first. It is right around, Thanksgiving weekend for us, so we're very busy over at the house. But yeah, that's all there is to say. Take care.